So what's gonna happen is that um, fundamentally you're doing a lot of like comparison. So um, you have the negative infinity and a positive infinity. So this comparison is just basically checking that are you like within like a valid value or not. So operation Z, where you compare the infinities, and once you're done with that, you say that like this with is like it fulfills like the core objective, which is to say that does it like fit for a binary search tree. That's what we're asking when we do the form of like comparison for here. So similarly, we go down here, we do a comparison, but I just feel that this operation Y is different from Z in the sense that there's this extra items that you are extra parameter that you're included into the formula comparison. Like, but fundamentally, you're still doing a a comparison. You're just bringing down because obeying the law of like binary search tree is that whatever goes to the left is gonna be like a lesser value, and whatever is on the right is gonna be a plus value. So in fact, here is a plus, and here is a negative. This route. So therefore, when you do the comparison, is that obviously you must be within range of like an item, which operation Z is making sure that it is like we are bringing a appropriate value into it, and so as such is that you come down to this path and you are actually checking whether if it's like some form of like appropriateness. So it must be more than negative infinity, right? So like the only item that like we are very much concerned is that it must fulfill the criteria of like less than. So it must be less than the root item. So therefore this is like the formula for operation Y. And now cool. And similarly, actually, when you go down to the right path, it's also doing the same operation Y, where you are just doing a comparison, but this time around you are following the positive route. So your value must be at least more than the root. And the other side is just making sure that it's within range. So if it's like less than infinity. And similarly, like how the root travels always left is a negative, here is a plus. Here is also the same thing. Here is a negative, here is a plus. You do the Y operation, where we go down to this route first. So it must obviously be more than your this node this time round, because it's always like based on like your values. It's always like based on previous node. And for this case, it's just basically based on like this node over here. So you are just making sure that it is like more than the previous, which is the 7, and if you want to see whether if it's like within range, if it's like less than the infinity over here, right? So sure, and that you can actually come down to this route over here, and that like it's on the negative route, so obviously that it must has been less than the previous node, which is a 7. But because you're saying that like you're comparing with like this sub item, that you actually do a extra base item, which is the base of the entire right subtree. It's because that your this sub tree is falling under this whole entirety of the right side. So in fact, you got to be more than this 5, like fundamentally. And with that, if this item is like a 4, this item, it doesn't fulfill the criteria of like y, and therefore you actually have to actually return the system if the item is like a false. Like other than that, it's usually the case of like just not doing anything, because I mean everything fulfills the criteria unless like something goes wrong, 出事了, then you do operation X, that you return that this item, it doesn't like fulfill the criteria of like being a binary search tree. Yeah, so that's pretty much everything in terms of like concept wise. I think one item to actually really take note is that I think this operation Y is quite a big one, and if I were to actually break it down, there's operation W in hand, that fundamentally whatever you're doing, you're sort of like doing a formula comparison, and operations G is that there's some form of memory value that is being passed down. So maybe say for example, like we've gone deep enough until like over here, right? But we are still following a formula that it's coming from the previous side of things. And I do think that if you can actually, if you were to actually look it, like whatever's over here is already being passed down to your previous node. So this memory, it really comes down to like the previous node. So having this item fulfilling the criteria for this, if you were to fulfill the criteria of this, when you get pass out here, if you fulfill the criteria of here, you are fundamentally fulfilling the criteria here. So when you get passed down over here, you fulfill the criteria here, you are generally fulfilling the whole entirety criteria. And at its core, you are just fulfilling the previous one. So your memory is just really comes down to the previous nodes, if you were to ask me. And I believe that operation N in this case is that there is some form of like smart maneuver map. So each time you go to like a new area, you are comparing with like a different set of item. Like say for example, like you go down left, you are comparing for less than. You're going to the right, you're comparing more than like the root. So I think with that, it just obeys the laws of like having some form of like smart maneuver map, where you do all this form of like comparison as such. So like whenever you go to like different areas, you are just maybe in this like maneuver system is that you are just changing how your formula is gonna look like. And for this case, it's like the formula for comparison. And if once we actually broke it down, we fundamentally see that there's an extra line, which is the entirety of the subtree, which is not which an extra item, because if as long as you base on your previous node, you are obeying the law of like this item, which we earlier talked about. And when you see this many amount of like operations, I usually like of all the characters that I've casted in the past, I feel that it just follows the rules of like having this the moment you talk about like multi operation within like each node you always have like all these different operations that's actually going on, right? And that you some form like you do some form of like a memory pass down to your next operation, and all these items, it really comes down to conducting of like a DFS, in my opinion. So all these are all the spells and DFS, like, it falls under the category of like the character of the tree. And whatever your Leetcode question for this case is asking, like, it's really, at the end of the day, it's trying to say that the core of things is that you want to actually fulfill the criteria of binary search tree. And when you want to fulfill this criteria, you have to do a lot of like comparisons with the different values. When you start comparing for every single node, it almost feels like every single node, that whatever you're doing over here, the comparison part, is that at the end of the day, the one that can actually compare everything with every node, it's using this DFS system, where you have like a multi-operation system with every single node. And you see like some form of like coincides with this character, spell, and the rulebook. So one reminds you of the other. And you will have like the brute force to actually fight against the main character. And for this case, I straight away see that if you were to do brute force, you're supposed to go for the negative route. You slightly go towards the right side. You are breaking the rule already, because whatever the rulebook is asking you to do is to obey the rules of like binary search tree. And if it wants to compare for like a negative value, you don't know where to go, you're in trouble. Whereas for trees, the character tree, it does know which side is which side, because it has like this smart maneuvering system where it goes to the correct sides of things, which fulfill the criteria of binary search tree. So with that, everything comes to an end.